Hey guys, and welcome back to another A-Level Maths revision video. And in this video today, we're going to take a look at the predicted paper for paper 2 in Pure Maths for the A-Level Maths. So, a bit of a tongue twister, but we got there. So this paper is just built on the advanced information that's been released by Edexcel to help you with your exams. I've used a mix of the topic tests and old exam questions from C1 to C4. So you should hopefully find this paper kind of a decent tool for revision, but don't obviously just rely on something like this to help you with your exams. I've tried to make the paper a good balance of, easy questions and challenging questions. There was kind of a mix in the feedback on the last paper in terms of difficulty, so I've tried to make this, a decent paper in terms of accessibility. But I'd definitely like to hear your feedback, how you found it. But other than that, I don't think I have really anything else to say. So let's jump straight into this predicted paper. Starting with question 1 here on our predicted paper, we have a question on the factor theorem. So we've been given our function f of x, and we've also been given that x plus 2 is a factor of f of x. And all we want to do is find the value of the constant a. So you should hopefully find this quite straightforward. There's only 3 marks for it, and there's not too much work to actually do here. All we need to know is that if x plus 2 is a factor of f of x, then what that means is f of minus 2 is equal to 0. So in that case then, if we substitute minus 2 here into f of x, replacing x with minus 2, and we set that equal to 0, then we should be able to solve for a. Okay, and that would give us the value of the constant a. So let's do that then. So we get 2 lots of minus 2 cubed minus 5 lots of minus 2 squared plus ax. So if x is minus 2, that's the same as minus 2a. And then finally we've got plus 8. And we know all of this is equal to 0 by the factor theorem. Okay, x plus 2 is a factor of f of x. So in that case then, all we need to do here is simplify this and solve for a. So minus 2 cubed, well that would be minus 8. And then we times that by 2, giving us minus 16. We've now got minus 2 squared. So minus 2 squared is 4. Times that by minus 5, we get minus 20. Minus 2a plus a, well that would give us minus a. And this is all equal to 0. Okay, so that's a 0. Simplifying this here then, we get minus 36 minus a equals 0. And therefore, to get a, we just need to take this minus a onto the other side, balancing the equation. So therefore, a is equal to minus 36 there. Okay, so that gives us the value of the constant a, and that gives us our solution to question 1. Moving on to question 2 now, we have a question here on the Trapezium Rule. And it's laid out in a pretty standard way, where part A we're just looking to complete the table, part B we use the Trapezium Rule, and then part C is just almost like a problem solving based on our solution to part B. So let's start with part A here. And all we're looking to do for part A is complete the table. Now sometimes you might be asked to find all the values in the table. In this case we only need to find one particular value, and that's when x equals 1. So to find y, we just replace x here with 1 in this given equation. So y is equal to a minus, so this is 2 to the power of x minus 1. So if x is equal to 1, that's 1 minus 1 there. Okay, so all we need to do now is simplify this. So we get y equals a minus, so 2 to the power of 1 minus 1 would give us 2 to the power of 0. And we know anything to the power of 0 is equal to 1. So what I get here is a minus 1 giving us 7. Okay, so in that case, when x equals 1, y is equal to 7. So that's the first mark complete. For part B then, this is now just an application of the Trapezium Rule. And notice here this integral is from 0 to 4, just like we have here for our x coordinates from 0 to 4. And it's the same equation as in part A. So simply all we need to do is use this table with the formula for the Trapezium Rule, and we can find our approximate area. So therefore, for the Trapezium Rule, let's give the formula first. So the formula for the Trapezium Rule is given as h over 2. And we times all of this by, so our first term, y0. And what you might see is the last term added at the end, but I always put the first term and the last term together. So y0 plus yn. And then we do 2 lots of all the other terms. So 2 lots of y1 plus y2, all the way up to the penultimate term, so all the way up to yn minus 1. Okay. Like I said, you might see this yn at the end, so it might be y0 plus 2 lots of everything else plus yn. I just like to put them at the beginning, just to keep them separated. Okay. So that's the formula we need for the trapezium rule. So now we need to know what h is. So h is given by b minus a all over n. Okay, where n represents the number of strips, and a and b are the limits on our integral. So a is the lower limit, so that's going to be 0 in this case. B would be the upper limit, which is 4. So therefore, replacing everything we need here for h, b is the upper limit, like we said, so that's 4. A is the lower limit, so that's 0. And then n is the number of strips. So how do we know how many strips we've got? Well, we go back to our table of values, and we count how many data points we've essentially got here. So I've got 1, 2, 3, 4, 5. But that doesn't mean we've got 5 strips. We do 1 minus this. So if I've got 5 data points essentially, then the number of strips is 5 minus 1, giving us 4 there. Okay, so what I get here is 4 over 4, which gives us 1. So in that case, h is equal to 1. So the outside part here would be 1 over 2. So if we replace everything here now with what we've got in our table of values, then what I get for my approximate value using the trapezium rule is going to be h over 2, so that's 1 over 2. And we put our square bracket in, so it's y0, so that's the first term, 7.5, plus yn, which is the last term, and in this case, that's going to be 0. So it's up to you whether you put that in. To keep it simple, I'll put it in here just to make it clear, but you don't have to, obviously. 7.5 plus 0 is just 7.5. And now we do 2 lots of everything else. So 2 lots of 7, 6, plus 4. So all these 3 added together. So 7 plus 6 plus 4. Okay. And if we evaluate this on our calculator then, what we get here is a half times the inside here of this square bracket, and if you evaluate this, this is 41.5. So 41.5 divided by 2, I'll times it by a half, and what you get here is 20.75 there. Okay, so the approximate value for this integral with respect to x is 20.75. So that's part B complete. That gets us the next 3 marks, and then finally we arrive at part C here, and we should have just about enough room to complete this. And what we've got here then is this figure 1, which shows a sketch of the curve C with this equation that we had in part A and part B. And we've got this region here R, okay? And that's what we're looking to find for part C. So we're going to use our answer to part B to find an approximate value for the area of R. Now, if we think about the trapezium rule has just found this area between 0 and A, which is 4. That's found that area there, okay? So, in that case then, it's found the whole area, okay? Well, we're looking for just this part here, R, this shaded region. So it makes sense then, if we just want the region R, so if we want the region R, this approximate area, then it makes sense that this is going to be approximately our area from part B, the whole area, minus this right angle triangle. Okay, so if we just make that clear, it's going to be 20.75 minus this, the area of this triangle here. Okay, and remember this will be a right angle triangle because it's got this perpendicular intersection here. So the y-axis meeting with the x-axis here, so it's definitely a right angle. So it's a right angle triangle with a base of 4 units and a height of 7 units there. Is it 7 units? Oh, sorry, 7.5 units. Ignore me, 7.5. Okay, so base 4 units, height 7.5 units. So therefore, the area is going to be base 4 times by the height 7.5, and we divide that by 2. So minus a half times the base, which is 4 times by 7.5. And if you evaluate this on your calculator, what you should find here for R is this is approximately, or our approximate value for the area of R is 5.75 there. Okay, and that gets us the final 2 marks and gives us our solution to question 2. Taking a look at question 3 now, we have this quite brief question here, taking a look at the number of bacteria in a liquid culture which is modelled by this formula. So there's 3 parts to it. Part A, just 1 mark, so let's have a look at this just to get us started. So in part A, we're asked to state the number of bacteria at the start of the study. So the formula we have is n equals 3,500 times 1.035 to the power of t. Now, if we're looking for the number of bacteria at the start of the scientific study, where t is the hours after the start of the study, then t in this case will simply be equal to 0. Okay? And there's a bit of a clue here in that it's only 1 mark. We're not going to be doing any kind of real calculations, very brief working. So in that case, n here is going to be 3,500 times 1.035 to the power of t, where t equals 0. And remember, anything to the power of 0 is equal to 1. So this part here is equal to 1. So I get n equals 3,500 times 1, giving me 3,500 there. Okay, so that gets our first mark. Like you can see, not too much work really to it. So that gets us part A. Let's have a look at part B now. And in part B, it says, find the time taken from the start of the study for the number of bacteria to reach 10,000, giving the answer in hours and minutes to the nearest minute. So in that case, what we're looking for here is our formula being equal to 10,000, where 10,000 is the number of bacteria. So what I've got then is 3,500 times 1.035 to the power of t is equal to 10,000. Okay. Now what we're looking to do here is solve for t. So the first thing I need to do is get rid of this 3,500, and because this is times in, then we do the opposite, we divide by 3,500. So therefore I get 1.035 to the power of t is equal to 10,000 divided by 3,500. And if we evaluate this on our calculator, I'll just simplify it by hand. What you should get then is 1.035 to the power of t is equal to 20 over 7. And then this works out as a pretty basic equation to solve. We're looking for the power of t, so we're going to now be using logarithms to find this. So I'm going to take the natural logarithm of both sides here. If I take the natural logarithm of this left-hand side and bring the t down in front using the power rule, then we get t times the natural logarithm of 1.035 is equal to the natural logarithm of 20 over 7. Okay? But remember, we just want the value of t, so we divide by the natural logarithm of 1.035. So therefore, t is equal to the natural logarithm of 20 over 7 divided by the natural logarithm of 1.035 there. Okay, so that gets us the next 4 marks, part B, and then finally we arrive at part C here. So we'll just need to clear the screen to have a go at part C. Let's have a look at this now. Now part C says use calculus to find the rate of increase in the number of bacteria when t equals 8. Given the answer, I noticed I made a slight mistake, or I missed something for part B. I gave the actual working for t, but I didn't give the answer. So t equals 30.517 hours. So I nearly missed that. But we want this in hours and minutes to the nearest minute. So if you just convert this, then this is 30 hours and 31 minutes. 30 hours and 31 minutes. Okay. There we go. I blame it because we nearly ran out of room. So part C. So we're using calculus to find the rate of increase. So when we see that word of increase and the rate, then we know we need to use differentiation. So what I need to do then is differentiate n here, this formula, with respect to t. So we're looking for dn by dt. Okay. So all we're simply doing then is just differentiating this right hand side here with respect to t. So the 3,500 is times in by this 1.035 to the t. So we will still get this 3,500 in front. So we'll keep that there for now. Now when you've got something like this where it's just a constant to the power of t, the thing that we're differentiating in this case, then we have a special result for that. That gives us a to this power, where a is this 1.035. So a is 1.035. So that's going to be a to the power of t. So it's going to be 1.035 to the power of t times by the natural logarithm of a, where a is 1.035. So that's a natural logarithm of 1.035. And we're looking for this now when the time t is 8 hours. Okay, that's what we're told here. So all I need to simply do then is substitute t equals 8. So t equals 8. So this is equal, or dn by dt is equal to 3,500 times 1.035 to the power of 8 times by the natural logarithm 1.035 there. Okay, now we put this into our calculator. What you should find here is that you get 159. So we're doing this in bacteria per hour to the nearest whole number, so that's going to be 159 there for the number of bacteria. So there we go. That gives our solution to part C. Okay, and the solution to question 3 overall. Taking a look at question 4 now, we have a question here taking a look at the modulus function and sketching graphs. So it's split into 4 parts here, so let's start with part A just to get started. So in part A, we're asked to sketch the graph of y equals, and we've got the modulus here of 2x plus a, where a is a positive number. A is greater than 0. So we need to show the coordinates of the points where the graph meets the coordinate axes. So what I'm going to do here is just do a quick sketch of an example. So let's just pick any example here where a is greater than 0. So let's say we've got y equals the modulus of, let's just say 2x plus 3. Okay, so 2x plus 3. Well, what we need to do is find where normally, let's just think about this first. So y equals 2x plus 3. Where would y equals 2x plus 3 cross through the y-axis and the x-axis? So the y-axis here would simply be 3. That's when x equals 0. So that's 2 lots of 0 plus 3. So it would cut through at 3. Let's say that's there. And in terms of the x-axis here, well, that's when y is equal to 0. So we get 2x plus 3 is equal to 0. So 2x would be equal to minus 3, and therefore x would be equal to minus 3 over 2. Okay, so it would cut through the x-axis, let's say there. That's minus 3 over 2. Okay, so if you was to sketch that then, this is just the equation of a straight line. So it's going to look something like this. Okay, so that's y equals 2x plus 3. Okay, but what we're concerned about essentially here is the modulus of 2x plus 3. So if I draw this in a different colour just to highlight this, well, when you're taking the modulus of the whole expression like this, y equals the modulus of 2x plus 3, then anything below the x-axis here, so this is the x-axis, this is the y-axis, anything below the x-axis gets reflected above. So we would have this part here, from this point here where it cuts through the x-axis all the way up, that would remain the same. However, anything below would be reflected above in the x-axis. So it's going to look like this, okay? It's not perfect, but you get the idea. So this red line here, or this red sketch I've done, that is y equals the modulus of 2x plus 3. Now, why are we doing these examples here? Because obviously our example is y equals the modulus of 2x plus a, where a is a positive number. So it doesn't matter kind of what a is, we just know it's a positive number. So it could be 2x plus 5, 2x plus 10, 2x plus 100. We don't know what it is, but we know what that's going to look like. Okay, so we can sketch this. So let's have a go at sketching this then. So if we sketch this, well, we know it's going to cut through the y-axis. So if we just write the equation down, so this is 2x plus a. And if we, again, if we just consider 2x plus a, well, it cuts through the y-axis when x equals 0. So 2 lots of 0, we just get left with a. So it will cut through here at, say, a. So that's a. And in terms of the x-axis, again, this is when y equals 0. So we get 2x plus a equals 0. And solving for a here, solving for x even, we get 2x equals minus a, and therefore x is equal to minus a over 2, or minus a half a. Okay, so it's going to cut through, say, here at minus a over 2. Okay, and it's going to look pretty much identical to this. Again, it's going to look like that going up, and anything below. So this would normally go beneath the x-axis, just like it did here, but because we're taking the modulus of the full thing, it will be reflected above. So it's going to look something like that. Okay, so that gives us our sketch there of y equals the modulus of 2x plus a. So that's part A done. Well, we've also given the coordinates of the points where the graph meets the coordinate axes, so that's fine. Part B then also goes on the same axes. So on the same axes, we need to sketch the graph of y equals 1 over x. So this is the reciprocal function. I won't lie, I always have great difficulty sketching this. So what I'm going to do first is, because we need this quadrant here, just get rid of that minus a over 2, and we'll just write that above. So this point here was minus a over 2. So the reciprocal function, it has this shape here where it starts right at the top, comes down, it kind of goes towards the x-axis. But I can never do it perfectly, so we'll give it a go. So obviously this is an asymptote here. It's going to look something like that. Again, it's not perfect. I'll do it in a different colour as well, just to make it clear that this is a different curve. So this should keep getting closer and closer. It doesn't touch the x-axis, remember it's an asymptote here, but it's going to look something like that. This is y equals 1 over x. And again, it also has part of the curve in this quadrant, and again, it's got the same idea where it looks like that. Again, I can never do it perfectly, but that one's actually not too bad. I'll take that one. So that's y equals 1 over x. So that's part B done. That was only 1 mark. But part C then says, explain how your graphs show that there is only one solution of the equation x times by the modulus of 2x plus a minus 1 equals 0. So how does that work? Well, we're going to have the solutions when, so let's just write this down. So we'll have a solution or solutions when these two graphs meet here. Okay, so when 1 over x, is equal to the modulus of 2x plus a. Okay, so if we times through by x here, what I get then is x times the modulus, so x times the modulus of 2x plus a is equal to 1. Okay, I've just times through by x, and therefore if we subtract 1 off both sides, what I get is the exact same as what they've got here. Okay, so that gives me x times the modulus of 2x plus a minus 1 is equal to 0. And what we can actually notice here, I can never do it in a different pen colour, is we only have one point where these two curves intersect, and that's this point here. Okay, so they only meet once. So that's how we know there's only one solution of the equation. So the graphs only intersect once, or only meet once. So therefore, that tells us there's only one solution. There is only one solution. Okay, and that's all we need to put there for part C, just showing that obviously we can rearrange this to be equal to this here, and because these curves only meet once, there's only one solution. So that's part C done. And now for part D, we're asked to find, using algebra, the value of x for which x times the modulus of 2x plus 1 minus 1 is equal to 0. So notice this is very similar now to what we've got here in part C. Now we know there's only going to be one solution, that's what we've shown here in part C, but we need to find that solution. So when you're solving modulus equations like this, we normally have to consider both parts. Okay, so what we do is we consider the positive part of the modulus function here, and we'd also include the negative part of the modulus function. Now here, as we're only getting one solution, we're probably not going to need both parts. We'll either just need the positive solution, or we'll just need the negative solution. Now, I always start with the positive one, just to make life a little bit easier, but it's up to you whether you start with the positive or negative. So let's just cut off everything here, just so we can make it clear where this question begins. So this is for part D now. Okay, so part D, we're doing down here in this bottom right corner. So x times the modulus of 2x plus 1 minus 1 equals 0. So like I said, it's up to you which part you take positive first. I'm going to take this as positive first. Okay, so what I would get here is x times 2x plus 1. Each part is positive. We've got the minus 1, and this is all equal to 0. So what happens now? Well, we just simplify this left-hand side here. So I'm going to multiply through x by 2x plus 1. So I get 2x squared plus x minus 1 is equal to 0. Okay. So now we look to see if we can factorize this. This is just a quadratic equation. We always check to see if we can factorize, and we actually can in this case. So if we factorize this, what we get is 2x minus 1 times x plus 1, and this is all equal to 0. So in this case now, I actually get two solutions here. So what I get then is 2x is equal to 1, so x is equal to a half, or we get that x is equal to minus 1. Okay, but clearly there's an issue here because we should only get one solution. So which solution do we omit? Well, if we think about what we got here in our sketch, we notice where these curves intersect, it's in this quadrant here, which means x must be greater than 0. So clearly x cannot be minus 1. X must be greater than 0, so we can't have that solution there. So x can't be equal to minus 1. So therefore, our solution is x equals a half. Okay? And from that point there, we're actually done with part D and question 4 overall. But just to make it clear, you could have took the negative solution. So if I just try and finish that off down here, what you would have got is x times, so it now would be minus 2x minus 1 equals 0. So what I've done there is I've took the negative of this, so it would be minus 2x minus 1, and we times that by x, we've still got the minus 1, and this is all equal to 0. So this would give you minus 2x squared minus x minus 1 equals 0. So if I take everything onto the other side, that would give me 2x squared plus x plus 1 equals 0. But this solution here has no real solutions, okay? So we know this one wouldn't work. So that's what would happen if you start with a negative. You'd find you've got no real solutions, and then you'd have to consider the positive part of the modulus function. Okay, so just to show what happens if you start with a negative, that's the issue there. Okay, so you get no real solutions. So your solution for part D should just be x equals a half there. Okay, so that gives us the solution there to question 4. Moving on to question 5 now, we have a question here on binomial expansion. And it's split into 3 parts. In part A, this is where the majority of the marks are found for this question. What we want to do is use binomial expansions to show that the square root of 1 plus 2x over 1 minus x is approximately 1 plus 3 over 2x plus 3 over 8x squared. So, the first thing we want to do with something like this is get it into an appropriate form such that we can use binomial expansions. In its current form here, we can't use any binomial expansions. Now, as this is a quotient, we've got 1 plus 2x over 1 minus x. Ignore the square root for now. We've just got 1 plus 2x over 1 minus x. What we want to do is write it as a product rather than a quotient. And to do that, we use the index laws that we're familiar with. So, keeping the square root in for now, what I've got is 1 plus 2x over 1 minus x. Okay. Now, we can write that as 1 plus 2x to the power of a half. Okay, remembering the square root of the quotient here is the square root of the numerator divided by the square root of the denominator. So that's 1 plus 2x to the power of a half times by now 1 minus x to the power of minus a half. Okay, so we're writing this as a product now rather than a quotient. So obviously this would be minus a half. And again, it's the square root of 1 minus x, but it's as a product now, so it must be minus a half. Okay. Now, in this form, we can go on to use the binomial expansions here on each individual product, essentially. So this 1 plus 2x to the power of a half, we can find the binomial expansion for that. And then do the same here for 1 minus x to the power of minus a half. Again, we can use binomial expansions for that. And obviously, to get our final approximation, we just times the results together then. So let's just write the formula that we need here. So this is in the form 1 plus. So this is 1 plus x to the power of n. So the formula here for 1 plus x to the power of n, well, that's given by 1 plus nx. And then we add, so this is the longer part, so it's n times n minus 1 times x squared. And this is all over 2 factorial. Now we can stop here because if we notice the approximation that we need to show, the highest power is x squared. Okay, is the highest power being a power of 2. We can stop once we get to x squared. So that's the form that we need. So if we write down 1 plus 2x to the power of a half first, so 1 plus 2x to the power of a half. Well, if we start with this, let's just write down what n is and what x is in this case. So n is the power. So our power here is just a half, so n is a half. And the x here, I'm being a bit loose with the rules of maths here, but what I'm saying then is our x is equal to this part here. So x is equal to 2x, okay? And let's just do the same for 1 minus x to the power of minus a half. You don't have to do what I'm doing here. I'm just doing it to make clear what I'm going to be doing in a moment and just lay everything out nicely. So again, n here is the power, so that's minus a half. And x in this case is minus x. It's always this part here, so x is equal to minus x. So now all I need to do is find the binomial expansion for 1 plus 2x to the power of a half, do the same for 1 minus x to the power of minus half, and then times them together. So let's start with 1 plus 2x to the power of a half. Okay. Now, like we've just said, all we need to do is use this formula here. So if we just highlight this, this is what we're going to be using. So in that case then, this is going to be 1 plus nx. So n is the power of a half, is the half here, that's the power. So it's going to be a half times by x, which is 2x. So a half times 2x. And now we add, so it's going to be n, so that's a half, times n minus 1. So a half minus 1, that gives us minus a half. And then we times that by x squared. So x in this case is 2x, so that's 2x all squared. And we divide this by 2 factorial. So we divide that by 2 in this case. 2 factorial is just 2, so we divide it by 2. So here now, all I need to do is start simplifying this. So we've got this 1 here, we can't do anything with that. A half times 2x, well, that would just give us x. So here, I've got a half times minus a half, so that would give me minus a quarter, minus 1 over 4. And we times that by 2x all squared, so that would be 4x squared. So in that case, that would give me minus x squared in the numerator, and then we divide it by 2, so what I get is minus a half x squared. So minus a half x squared. Okay, and like we said, we don't need to go past this. The highest power here is a power of 2. Okay, so this is absolutely fine. We now repeat this for 1 minus x to the power of minus a half. So 1 minus x to the power of minus a half. Again, we just use this formula now. So it's going to start off with 1 plus nx. So n is minus a half, and then x is minus x in this case. So that's minus a half times minus x. Now we add. So it's n again, so it's going to be minus a half. Now we subtract 1 from this, so minus a half minus 1, that gives us minus 3 over 2. And then we times this by x squared. So x in this case is minus x, so that's minus x all squared. And again, we divide this by 2 factorial, which is 2. Okay? And again, all we need to do here is simplify all of this. So we get 1, we can't do anything with that at the moment. We've got minus a half times minus x, so that would give me positive a half x. Okay, minus a half times minus x gives us positive a half x. And then this part here, again, just cleaning all this up, I've got minus a half times minus 3 over 2. So that's going to give me positive 3 over 4. I've then got minus x all squared, so that would be positive x squared. And then we divide it all by 2. So when we simplify that, we get 3 over a x squared. Okay. Now, what we want to do is find the products of these expansions. So what I need to do then is consider the products of these 2 expansions. So let's just do this part in a different pen colour to make it clear. So what I've got now is 1 plus x minus a half x squared. That's this expansion here. And we'll do this part in a different colour. Let's do that in blue. So this part now, again, we write this as a product. So we're timesing these together. So that's going to be 1 plus a half x plus 3 over 8 x squared. Okay. And if we just write the product here, or the result of this product, in a different pen colour, just to make everything clear then, what I'm going to do is I'm going to go through each term, and anything greater than a power of 2, we can omit. We don't want that because we don't include it in our approximation here. So if I start with this 1 and I times it by everything here, so 1 times by 1 gives me 1. 1 times by half x gives me a half x. And 1 times 3 over 8x squared gives me 3 over 8x squared. So that seems easy enough. We then move on to x here. Okay, so we do x times 1, which gives me positive x. Okay, that doesn't look very clear. Let's just try that again. So like we just said, let's try and get it right this time. So x times 1 would give me just x plus x. I've then got x times a half x. That would give me a half x squared. And if you think about it, we can stop here for x, because if we did x times 3 over 8x squared, then we would get 3 over 8x cubed. Okay, so we don't want that term. We stop at x squared, so we don't need to bother with that. So we're complete with the x, and we move on finally to minus a half x squared. And if we think about it, all we've got to do here is times minus a half x squared by the 1. If we times it by anything else in this blue bracket, then it will be greater than a power of 2, and we wouldn't include it. So finally, minus a half x squared times 1 gives us minus a half x squared. So here now, we just look to see what we can cancel. What we should get is this result here, okay? Well, I've got a half x squared minus a half x squared, so they just clearly cancel. And then if we just look here, we just want to keep simplifying. So I've got 1, which is what they've got, so that looks good. I've then got a half x plus x. So a half x plus x, well, that's the same as 2x over 2 plus a half x. That would give me 3 over 2x. So plus 3 over 2x. And then finally, 3 over 8x squared. So plus 3 over 8x squared. Okay, and that's exactly what we wanted to show for part A. So as required there. So that gets us the first 6 marks for this question. So hopefully that wasn't too bad. So that's part A done. So let's just clear the screen dead quick so we can carry on with B and C. Moving on to part B now, just for 1 mark, so hopefully it shouldn't be too much work. We just have to find the exact value of the square root of 1 plus 2x over 1 minus x when x equals 1 over 10. So all I simply need to do here is substitute this value of x into this expression here. Okay. The other thing we've got to be careful of is we need to give the answer in the form k root 3. Okay. So let's start by substituting that in. So part B here, so that's the square root of 1 plus 2 lots of 0.1 all over 1 minus 0.1. So if we just simplify this for now, this is the square root of 1.2 in the numerator, and then we divide this by 1 minus 0.1, which is 0.9. Now you could put this into your calculator, and your calculator might give you that in the exact form that we're looking for here. If your calculator won't do that, then we just need to do a bit of extra work to get in that form. Okay, so what I could do here, if you think about it, this is just the same as the square root of 12 over the square root of 9. Or you could write that as the square root of, how could you write that? So you could write that as 2 individual square roots. You could write that as the square root of 12 over 10 divided by the square root of 9 over 10. You could do it that way as well and simplify like that. I'll just do it with the approach of keeping this as 12 over 9. Okay, so we just times top and bottom here by 10. Okay, so all I do now is I split these square roots up individually. So the square root of 12 over 9, we could write that as the square root of 12 divided by the square root of 9. So that's the square root of 12 divided by the square root of 9. These are quite large square roots. I don't know why. So we just simplify each one individually. The square root of 12, well, we could write that as root 4 root 3. And the square root of 9 we know is 3. So in that case then, a root 4 root 3, well, root 4 simplifies to give us 2. So what we get is 2 root 3 over 3 there. Okay, which is what we wanted. We wanted this to be in the form k root 3. So in this case, k is equal to 2 over 3. Okay, so that gives us the solution there to part B. And now we move on to part C. So for part C here, what we're asked to do is substitute x equals 1 over 10 into the expansion given in part A. So even if you couldn't do part A, you can still want to do part B and C here. And what we want to do then is find an approximate value for the square root of 3. We're going to give the answer in the form A over B, where A and B are integers. So what we do here to start with is we know that this part, when you substitute 1 over 10 in, is equal to this here. So what we could say then is 2 root 3 over 3 is equal, and all I need to do now is substitute 0.1 into this expansion here. So that's going to be 1 plus 3 over 2 times 0.1, 1 over 10, and then we do 3 over 8 times 0.1 squared. Okay, so what we need to do now is evaluate this right hand side here. So I get 2 root 3 over 3 for the left hand side. Still, we'll just leave that as it is for now, and this is going to be equal. So if you evaluate this right hand side in your calculator, keep it in exact form, what you get here is 923 over 800. Okay, so it's over 800, and what I want is root 3. We want an approximate value for root 3. So all I need to do now is change this left hand side here. Instead of it being 2 root 3 over 3, we just want it to be root 3. So in that case, what I'm going to do then is times 3 by 3 and then divide by 2. Okay, so therefore root 3 is equal to 923 over 800 times by 3 and then divided by 2. Okay, so in that case, what I get for root 3 is 2,769 over 1,600. Okay, and that's in the correct form there. So we've got it in the form A over B. What I'm going to say here is a piece of advice for questions like this is to put this into your calculator. Okay, so if we just quickly do this, 2769, so 2769 divided by 1,600, what I get for that is that that's approximately, so 2769 over 1,600 is approximately 1.730625. Now root 3, if we just find what root 3 is, these two answers should be very, very close. If we get something that's wildly different, then we've done something wrong. So root 3, put that into our calculator, and what we get here is 1.73205, 08, and so on. Okay, so like we can see here, this is 1.730625, and this is 1.7320, and so on. So they're pretty close, right? That's 1.73, that's 1.73. So that's pretty good. But obviously, if this 2769 over 1,600 was completely different, let's say we got 1.28 or something, then you'd know you'd done something wrong. So always double check at the very end that your approximation is pretty close. If it's not, double check your working. Okay. So that gives us the solution there to part C and to question 5 overall. Moving on to question 6 now, we have a question here on the Newton-Raphson method. And this is a pretty standard question, like most Newton-Raphson questions, so you shouldn't find this too tricky as long as you're familiar with the formula that we use for the Newton-Raphson iteration. So I've also included the formula book here, or the relevant section in the formula book for the Newton-Raphson method. So it's under numerical methods, and you will be given the Trapezium Rule formula and then the Newton-Raphson formula here. Okay, so we've got our function f of x here. We're told that we have a root beta of the equation f of x equals 0, and it lies in this interval here. So we're going to take 3.5 as our first approximation to beta. We need to apply the Newton-Raphson process once to f of x to obtain a second approximation to beta. Okay, and we're going to give our answer to 3 decimal places. So if we start with this here, then we've got f of x, and we also need f prime. Okay, we need to differentiate f of x here. So if we've got f of x, what I'm going to do is just write this in index notation. So this is 2x to the power of a half. The only thing that we need to change then is this minus 6 over x squared. So we can write that as minus 6x to the minus 2, and then we've got minus 3. Now we need to differentiate this here with respect to x. So we go term by term. So that gives us f prime of x. Well, 2x to the power of a half. The half comes down in front and we times it by the 2, so that would give us 1, or just we're going to write that as x, and then we subtract 1 off the power. So if that's power of a half, then we can write that as minus a half. Okay, we've then got minus 6x to the minus 2, so minus 6 times minus 2 gives us positive 12, so that's plus 12 x, and then we subtract 1 off the power, so that's minus 3. And then finally, this minus 3 here, if you differentiate that, that's a constant, that would just become 0. Okay, so that's what we get there when we differentiate. And this 12x to the minus 3, we can write that as 12 over x cubed if you want. Okay, so that's 1 over the square root of x plus 12 over x cubed. Okay, so that's what we've got so far. What we need to do now is apply the Newton-Raphson iteration for solving f of x equals 0. Okay, so in that case, what we're told is 3.5 is our first approximation. So in that case, what I need to do is find f of 3.5, that would be my numerator here, and then we need to find f prime of 3.5. So f of 3.5, well, all we do then is we simply substitute 3.5 here into the x for f of x. So that's going to be 2 lots of 3.5 to the power of a half minus 6 over 3.5 squared minus 3. Okay, and if you put that into your calculator, you should get something that's very, very close to this, or depending on your accuracy, you're going to get 0.25186, so on and so on. Now, for now, I'm just going to leave it like this, but when you're putting this into your calculator, when you're calculating this, you need to keep as much accuracy as possible. Okay, so 0.25186, so on. Now we work out f prime, so f prime of 3.5. Again, we just substitute 3.5, but this time into f prime of x. That's going to be 1 over the square root of 3.5 plus 12 over 3.5 cubed. And if you do that correctly, what you should get here is 0.81441, so on and so on. Okay, and again, when we put that into our calculation later, we need to keep as much accuracy as possible. Okay, so we've got x naught. We know x naught is 3.5. Okay, what we want is x1. So therefore, x1 is going to be equal to xn. So n in this case is 0. So it's going to be 3.5. That's my previous term. Minus. So it's f of xn. So that's f of x naught, which we've just worked out here. That's f of 3.5. So in the numerator, we put this term here. So 0.25186. And again, keep whatever accuracy you've got in your calculator there. Okay. And we divide this by f prime of xn. So that's f prime of 3.5. Okay. So we divide this by 0.81441. And again, just keep as much accuracy as your calculator will give you. And all we need to do now is evaluate this on our calculator. Okay, and obviously make sure we give the answer to 3 decimal places. And if we do that correctly, we've got our solution. So therefore, for x1, what you should get here when you evaluate all of this is 3.191 there. Okay, and that's to 3 decimal places. So let's just write that down. 3 decimal places. Okay. And there we have it. So that gives us our solution to question 6. Taking a look at question 7 now, we have a question here on functions, and this question is a bit of a mixed bag. There's a couple of pretty standard parts, which you should find hopefully quite straightforward, and then there's some certainly tricky parts on this question, particularly in part D. So let's start with part A here, and hopefully should be one of the straightforward parts. Just 1 mark though, but we want to write down the range of f. Now remember, the range is the output values, so if we just take a look at the sketch here of f of x, then we can hopefully see that quite straightforward. Okay, so it doesn't go below the x-axis here, so that means the lowest possible value in our range here must be 0, so that's going to be 0, and we use f of x here to represent the range, and then the highest possible value here is at 10. Okay, we know this is -2, 10. So the largest output value, the largest y value we take is 10. Okay, so the upper bound here would just be 10 for our range, and that simply gives us the range there. Okay, so that's part A done, getting us the first mark in this question. Now with part B here, this part can cause issues. So this is a composite function of f of 0. Now we don't know specifically the function f of x. Okay, we just know this figure 1 here gives us a sketch of the graph of y equals f of x. So we need to use the graph here to find f of 0. And to do this, let's just consider f of 0 first. Okay, so what's f of 0? Well, if we look at the graph here, f of 0 is this point here. Okay, but we don't know whereabouts on the y-axis this specifically is. It doesn't state it anywhere. Okay, so we need to figure out what this point represents, or what the value of this point is. So there's two ways of doing this. We can either use the symmetry from -2 to 2 here, okay, over this interval from -2 to 2, or you can just find the gradient of this straight line here. Okay, so because this goes from -210 to 2, 0, so this is 2, 0 here, then we can simply find the gradient. So m would be equal in this case to 10 minus 0 all over -2 minus 2 there. Okay, so that's going to give us 10 over -4, which is the same as -5 over 2. So what that tells us then is for every 1 unit we go across, so when we go to -1, say here, then we go down 2.5 units. Okay, so we'd go from 10 to 7.5, which might be, say, there. Okay, so that would be 7.5. And then we go across 1 more unit to 0, and then we go down 2.5 units, and this must be 5 there. Okay, so f of 0 is equal to 5. So that's the first part. But now we need to find f of 5. So we found f of 0, and f of 0 now goes into f again. So f of 0 is 5, so what we're looking for now is f of 5. Okay, so f of 5 is going to be somewhere over here. Let's say that's 5. So what we're looking for is this value. We go across here. Okay, that's what we're looking for now. So again, this comes back to the question of how do we figure out what this is? Well, in this case, it makes sense to think about this interval here. So if I just use a different pen colour to represent this, let's use blue here. What I'm thinking about is this interval here. So from 2 to 6. Okay, well, that's 4 units. Okay, so that's 4 units. But what we want is 5. Okay, that's what we're looking for, f of 5. So if we think about it, from 2 to 6, that's 4 units. But if we're looking for 5, that must be 3/4 of it. Okay, it's 3/4 of the way along. So again, if I use a different pen colour just to highlight that, that's going to be 3/4 of the way. Okay, from 2 to 6. So in that case, if we think about the height of 6 here, okay, we go up from 6 till we get to here, and we go across. We arrive at this point here, but we know what this point here is. Okay, we know when x is 6, that has a height of 4. So this is 4 here. Okay, so if we know from at the point 6 here that we get an output of 4, in that case then, if we think about this, this must be 3/4 of the way along, which also means it will be 3/4 of the height there. Okay, so f of 5, we just go back to our original pen colour, is going to be 3/4 of the height that we had here. So it's going to be 3/4 of 4, and 3/4 of 4 would simply give us 3 there. Okay, so we know this point here is equal to 3. So therefore, what we can say then is f of 0 is equal to 3. Okay, so that gives us part B there for just 2 marks. You know, that can cause quite a few issues. You've got to think about it a little bit. But that's part B done there. Okay, now we move to part C here, and part C is 3 marks and should be hopefully quite straightforward. We've just got a function g here, g of x, and we just need to find the inverse for this. Okay, so you should hopefully find this quite straightforward. So if we just write down g of x first, so I've got g of x, so g of x here, well, that's going to be 4 plus 3x, and that's going to be all over 5 minus x. Okay, what we do then is we change g of x to be y, so I've got y equals here, and then we write down this again, so it's going to be 4 plus 3x all over 5 minus x. And what I want to do now is rearrange this equation, this right hand side, to be in terms of x. Okay, so the first thing I'm going to do is time through by this denominator, so I get y lots of 5 minus x is equal to 4 plus 3x. Okay, so 4 plus 3x. We're going to expand this left-hand side here, so we're going to times through by y So that gives me 5y minus xy is equal to 4 plus 3x. Okay. And like we said, we're making x the subject here. Okay, so I need to get the x's on one side and put everything else on the other side. Now I'm going to take this xy across to the other side, just so we keep that positive rather than having both of them negative. So we finish that up here then. What I'm going to get then is 3x plus xy. So what I've done now is put the x's on one side, so 3x plus xy. And I'm going to get rid of this 4 on this side here. We don't want anything else with the x's, so I get 5y minus 4. Okay. We said we wanted to make x the subject, so this left-hand side here now is pretty close. We just need to factor an x out and then divide by whatever's multiplying through. So we get x lots of 3 plus y there, okay, because x times 3 gives you 3x, x times y gives you xy. And this is still equal to the right-hand side, which hasn't changed, 5y minus 4. And then finally, if we divide through by 3 plus y, we get x on its own, and we've made x the subject. So x is equal to 5y minus 4 over 3 plus y there. Okay. And all we need to do now is actually give it in the correct form. So we wanted to find the inverse of g of x, so g inverse of x. So all we need to do now is replace x here with g inverse of x. So that's g inverse of x. And that's going to be equal now, and all we do here now is change the y's to be an x. Remember, this is an inverse function in terms of x, not in terms of y. So that's going to be 5x minus 4 all over 3 plus x there. Okay, and once you've got that result there, you've got your 3 marks. Okay, so like I said, part C should be pretty standard. You've just got a function g. We then go on to find the inverse of g. Okay, so nothing really, to kind of throw you off there for part C, I don't think. Just finding the inverse function. So that gives us the solution to part C. I'm moving on to part D here. I accidentally messed up the recording, so I'm going to do D separately here. So we're looking to solve the equation gf of x is equal to 16. Now, this part D here is quite tricky, and it requires a bit of thinking about how to actually solve this composite equation. So I've got gf of x equals 16. So this is part D. And the reason this is quite tricky is because we can't go on to solve this composite function equation in the standard way. And the reason for that is because we don't know explicitly what f of x is. Okay. So there's a few different ways of actually doing part D here. So you might do a different way of tackling this problem. But the way I'm going to do it is based on part C. And it's no coincidence that in part C we found the inverse here, so g inverse of x. Because what we're going to do now is we're going to use the inverse here and get rid of g on the left-hand side. What I want here is just f of x on the left-hand side. Okay? If we can just get f of x on the left-hand side, then we can use our sketch here in figure 1. So the way we do this is by timesing through, but on the left-hand side and the right-hand side, so on both sides of this equation, by g inverse. And what happens when we do that is we're going to get on the left-hand side g inverse times g, and these will cancel. This just gives us what we call the identity. So these cancel, and we just get left with f of x. So I times through both sides by g inverse, so we get g inverse times g of f of x. And remember, we do it to the right-hand side here as well, so that gives us g inverse of 16. And like we just said, they cancel on the left-hand side, so they cancel, and what I get left with then is f of x is equal to g inverse of 16. So we need to use our inverse function from part C to find g inverse of 16. So if we just write g inverse down again, so g inverse of x, well, that's equal to 5x minus 4 all over 3 plus x there. Okay, so if I want g inverse of 16, then we just substitute 16 into this. So that's going to be 5 lots of 16 minus 4 all over 3 plus 16. Okay, so this is going to be equal to 18 minus 4, so that gives us 76 in the numerator, and 3 plus 16 gives us 19 in the denominator. So we get 76 divided by 19, which is equal to 4. So what I've got now is f of x is equal to g inverse of 16, but g inverse of 16 is equal to 4. So g inverse of 16 is equal to 4. So what I've actually got now is f of x equals 4. So if we think about this, if we look at our figure 1 here, what we're looking for is the points where the function f of x is equal to 4. So we get 2 points. We get this point here, and we get this point here. Okay. And we already know this point. This is 6, 4. Okay. So when f of x is equal to 4, x is equal to 6. Okay, we can see that from figure 1. But what we are interested in is this second solution here. What's this? Okay, that's what we're looking for. And there's a few different ways you can tackle this now. You can use similar triangles, or you can use the equation of this line here. So this line here, okay, the equation of this line. And that's the way I'm going to tackle this. I'm going to find the equation of this line. Now, we already know the gradient of this line. We found that in part B, I think it was, part B. So the gradient of this line, it worked out as minus 10 over 4 or minus 5 over 2 there. Okay, so if I've got the gradient, I know, a point on that line, I can easily find the equation of the line using y minus y1 is equal to m lots of x minus x1. Okay, so if I use this point here, where it cuts through the y-axis, this is 0, 5. Seems straightforward enough to just use this point here. In this case then, what I get is y minus 5 is equal to m, which is minus 5 over 2, times by x minus x1. Well, x1 in this case is 0, so it's going to be x minus 0, which you don't need to write. You could just do minus 5 over 2 times x, but I'll write it just for clarity. So finding this then, what I'm going to get is y minus 5, but we can take that 5 onto the other side, or that minus 5 onto the other side, so it becomes plus 5. So what I get then is y equals minus 5 over 2x plus 5. Okay, so what I find there is the equation of this line. So this line here is y equals minus 5 over 2x plus 5. Okay, now if we know the equation of this line, if I say that y is equal to 4, that's what we're going to do here, and substitute into this equation, then I can solve for x, and then we then know what this point here is. If we call that, say, z, okay, we can then go on to find z. So, like we just said, we set y equal to 4, so I get 4 is equal to minus 5 over 2x plus 5. So, if we subtract 5 off both sides, in fact, I think it's easier if we take the minus 5 over 2x onto the other side, and then subtract 4 off both sides. So we get 5 over 2x is equal to 5 minus 4, giving us 1. I then times through by 2, and I get 5x equals 2, and we divide by 5. Or you could just divide through by 5 over 2 here. 1 divided by 5 over 2 gives you 2/5. So therefore, x is equal to 2 over 5. Okay? So we know this point here, z, the x-coordinate of that is 2 over 5. So we get rid of that. That's 2 over 5 at that point there. Okay? Now, like I said, there's a few different ways you can tackle that last part. You can use similar triangles, or you could do it using this equation here that we did. Either way gets you full marks as long as you can get the correct x-coordinate there. So definitely not an easy question. Like I said, there's 2 solutions for part D there. X equals 6 and x equals 2/5. So just be very careful that you make sure you give this solution as well. Do not forget it. So x equals 6 as well. So definitely not the easiest question, but we got there. So that's the solution to question 7. Moving on to question 8 here, we have a question on differentiation from first principles. So we've been given the curve C, which has this equation, y equals 2x cubed plus 5. We're told the curve C passes through the point P, which has coordinates 1, 7. And we need to use differentiation from first principles to find the value of the gradient of the tangent to C at P. So before we start this, let's just recall the formula that we use for differentiation from first principles. So in this case, dy by dx is equal to the limit as h tends to 0. So that's the limit as h tends to 0. And I'm going to put all this in a square bracket here. So this is f of x plus h minus f of x. This is all in the numerator. And then we divide this by x plus h minus x. Okay, so that's the formula that we use here for differentiation from first principles. Now, we just think about this problem before we even start using first principles. If we're differentiating this equation here, okay, that would give us dy by dx. And this is a straightforward equation to differentiate. Term by term here, if we differentiate 2x cubed with respect to x, that would give us 6x squared. And the 5 here, that's a constant, so when you differentiate a constant, it becomes 0. So we just end up with 6x squared when we differentiate y here. And if we're looking for the value of the gradient of the tangent to c at p, we simply need to substitute this x coordinate here in. Okay, we don't need to find the negative reciprocal or anything like that. We simply need to substitute that point in. And that would give us 6 lots of 1 squared, which is equal to 6. So we know what we should get at the very end of this question here. We should get 6 as our value of the gradient of the tangent to c at p. But we need to do that using first principles now. So applying this formula here, then what we get is dy by dx. So we get dy by dx is equal to the limit as h tends to 0. So as h tends to 0. And again, I'm going to use the square brackets here just to kind of keep everything separated. So this is f of x plus h. So in that case, that's going to be 2 lots of x plus h cubed. So 2 lots of x plus h all cubed, just using our equation here for c. So that's curve c with this equation. So that's 2 lots of x plus h all cubed. And then don't forget the plus 5. And now we minus f of x. So f of x is our equation here. So that's minus 2x cubed plus 5. And this is all over h, because notice this is x plus h minus x. So they cancel, and we just get left with h. So this is all over h. Okay? So that's the first step of our working here. And the first thing I notice is that I've got this x plus h all cubed. So we need to find that expansion. So the easiest way to do that, or the quickest way, would be to use the binomial expansion. You can do it by hand, expanding that bracket 3 times. There's nothing wrong with that, it's just a long way of doing it. So using the binomial expansion here, I won't show the binomial expansion, I'll just show the result that you should get. So for x plus h all cubed, then what you get here is x cubed plus 3x squared h plus 3x h squared, and then finally h cubed there. Okay, so I'm now going to replace that back in here and times it by 2, and then we need to add the 5, and then we minus 2x cubed plus 5. Okay, and we're going to look to simplify that as our numerator. So in that case then, what I get here is the limit as h tends to 0 again. You'll notice it gets a little bit tedious, keep putting the limit in, but do include it. It is important here when we're differentiating from first principles. So we've got x cubed, so we times that by 2, so I get 2x cubed. So we get 2x cubed. We've got 3x squared h, we times that by 2, so that would give me 6x squared h. We got 3x h squared, that would give me 6x h squared. We get 6x h squared. And then finally we've got h cubed, so we times that by 2, so that gives me 2h cubed. We've also got the plus 5 here. We can't forget that. We've got plus 5. And now we've got minus 2x cubed. So minus 2x cubed. And we've got minus 5. Okay, so that's my numerator. And this is all over h. Okay. So here, if we simplify the numerator first, well, I've got 2x cubed here and I've got a minus 2x cubed here. So they cancel. We've got plus 5 here and we've got minus 5 here. Okay, and from that point there, I'm pretty sure nothing else cancels. No, perfect. So what we've got here then is the limit as h tends to 0 of, we've got 6x squared h, so 6x squared h. We've got 6x h squared, and then finally we've got 2h cubed, so 2h cubed, and this is all over h. Okay. So here the next step now is to cancel these h's, because this is 6x squared over 6x squared h over h. If you split these up over h separately, so I'd have 6x squared h over h, I'd have 6x h squared over h, and I would also have 2h cubed over h. That sounds weird to keep saying, So if we cancel here, it would cancel there. I would get left with just h there, and I would get left with h squared there, or 2h squared, I should say. Okay, so what that would look like then is the limit as h tends to 0. This time now, we'd get 6x squared. Okay, that h would cancel there. This time now, this h squared would just become h, so we get plus 6xh. And then finally, this 2h cubed would become a squared. Okay, and we get 2h squared. Okay. And now, all we need to do is actually consider the limit. So this limit is when h tends to 0. So as h tends to 0 here, this term here will tend to 0, and this term here will also tend to 0. So what I get left with then is 6x squared. So this is dy by dx, so dy by dx. And notice now, our dy by dx is exactly what we got up here. Okay, we also got 6x squared. So we know our differentiation from first principles has gone correct here. All we need to do now is substitute this x coordinate in here of 1. So when x equals 1, dy by dx, when x equals 1, is equal to 6 lots of 1 squared, giving us 6 there. Okay, so that gives us the value of the gradient of the tangent to C at P. So that gives us our solution there to question 8. Moving on to question 9 now, we have a question here taking a look at finding the area under a curve, specifically by parametric integration. So we've got the curve C, which has these parametric equations here, and then we've got the finite region R shown shaded in figure 2. And this is bounded by the curve C here, the x-axis, and then these following lines here. So x equals a natural logarithm of 3, and x equals a natural logarithm of 5. And in part A, pretty standard, we want to show that the area of R is given by this integral here. So what we want to do here, the very first thing we want to do is find our new limits. Now we can actually see from the integral what we should get. We should get the lower limit being 1 and the upper limit being 3. So how do we do this? Well, what we've got here is x equals the natural logarithm of 3. That's going to be our lower limit here. So if x is equal to the natural logarithm of 3, okay, that's this line here, x equals a natural logarithm of 3, and we know that x is equal to the natural logarithm of t plus 2, then what we can say here is the natural logarithm of 3 is equal to the natural logarithm of t plus 2. Okay, and then clearly we can see here that these two sides of the equation must be equal. That sounds silly, but obviously this is what an equation shows. So in that case, to make these equal, in that case, t must be equal to 1. And that's where we get the lower limit then. So that gives us the lower limit here of 1. We just repeat this now with x equals the natural logarithm of 5. And in that case, the natural logarithm of 5 is going to be equal to the natural logarithm of t plus 2. And again, these two sides must be equal. So in that case, t must be equal to 3. So the new limits are 1 and 3, which is exactly what we've got here. So we're off to a good start. We've got our new limits. Now, when we're going to be doing parametric integration like this, the region that we're looking to find here are, well, this is going to be equal to the integral. And for now, I'm going to keep the original limits of ln3 and ln5. So the natural logarithm of 3 and the natural logarithm of 5. And this would be y dx. But when we're using parametric integration like this, then we have a standard result for this. And once we transform our limits here, as we've done here, then replacing these limits of lower limit being 1 and the upper limit being 3, then the standard result that we need here is y dx by dt dt. Okay, this is a standard result here for parametric integration. So therefore, we need to find dx by dt. So we need dx by dt. Okay, that means we need to differentiate x here with respect to t. Well, as this is the natural logarithm of t plus 2, well, in this case, if you were to differentiate this t plus 2 here, that would give you just 1. So in that case, what we're simply going to get here is 1 over t plus 2. Okay, so nothing complicated about that. We just get 1 over t plus 2. So that's dx by dt. So what we've got here now is everything we actually need. We already know y. Y is equal to 4 over t squared. So therefore, r, in this case, is the integral from 1 to 3 of y, which we just said there is 4 over t squared. And then we times this by dx by dt, which is 1 over t plus 2. And this is all with respect to t, so we get dt. Okay. Now, we're pretty much there. We just need to write it in the form that they've got. So in that case, we get r is equal to the integral of 1 to 3. And in this case, we're just going to get 4 as our numerator. 4 times 1, giving us 4. And then our denominator, we get t squared times t plus 2. So t squared times t plus 2 there. Okay, and that's all with respect to t. Okay, and that is as required. So that gives us the first 3 marks there. So hopefully not too bad. But if you couldn't do part A, you don't need to panic too much. You can still go on to answer part B and part C. Okay, so that's part A done. Let's clear this now so we can have a go at part B. So part B is a bit longer, a little bit more complicated. So let's have a look at part B. So like we just said, you can have a go at part B even if you couldn't get part A, because they've given you the new integral. Okay, so what we need to find now is the integral here from 1 to 3 of 4 over t squared times t plus 2. Okay, so in this case now, what we need is the use of partial fractions. Okay, and a bit of a clue in that, if you couldn't spot it straight away, is this result here. Because we've got the natural logarithm of b, at some point I would imagine we would need partial fractions, and we do need partial fractions here. So if we get this in the correct format then, notice here we've got this t squared. So when we write this as partial fractions, we're going to get a over t plus b over t squared. So this way you've just got to be careful. And then finally the last term here is this t plus 2. So we get c over t plus 2. Okay. So now we need to use partial fractions here and find the value of a, b, and c. So to do this, we get everything over a common denominator. In this case, this a here, well, what I need to times a by is t. This is just a denominator of t, so that must be another t, and then t plus 2. So I get a t plus 2. Well, b here is already over t squared, so I only need to times that by t plus 2. So we get b lots of t plus 2. And then finally for c here, that needs to be t squared. This is over t plus 2, so we just need to times it by t squared. So we get c lots of t squared. And this is all equal to the numerator, which is 4. Okay. So here now we need to eliminate some of the t's. So in that case, the way to do this is just to look at each of the individual letters. So I've got A, B, and C here. So for example, if we said t is equal to minus 2, that would eliminate this B here, and it would eliminate this A here, because if t is minus 2, this would be 0, so we times A by 0. Same here, B would be times by 0. And what we just get left with then is just C, and we can go on to solve for C. Okay, so like we just said, these two parts here are equal to 0. So we said t is minus 2, so that's minus 2 squared times by C. So I get 4C is equal to 4, so therefore C is equal to 1. Okay, so C is equal to 1. We now repeat this again. So for example, if I said t is equal to 0, because if I set t equal to 0, this c cancels here, c times 0 squared, and this is a times 0 here, so this would cancel. I just get left with b then. So that's b times 0 plus 2, giving me 2b is equal to 4. And again, just solving for b here, we get 4 over 2, giving us b equals 2 there. Okay. And then finally, we just need the value of a here. Now, we already know b and c, so I just need to substitute something sensible in here. So if I just say t equals 1, so when t equals 1 then, for example, well, I get a times 1, so I just get a, and then 1 plus 2. So I get 3a. This is 1 plus 2, so I get 3b. So 3b. And then finally, c times t squared. So if t is 1, I just get plus c. And this is all equal to 4. Now we know what c and b are, so we get 3a. B is equal to 2, so 3 times 2 gives us 6, and c is equal to 1, so I get plus 1. And this is all equal to 4, so therefore we get 3a plus 7 is equal to 4, so therefore 3a is equal to minus 3. So 3a is equal to minus 3, and therefore a is equal to minus 1. I thought I'd made a mistake somewhere, but no, that's all good. So a is equal to minus 1. And that's everything we needed for our partial fractions. So now that we've found the values of a, b, and c, we can set up our partial fractions. So make sure you've got this line at the top up here with the partial fractions. I'm going to clear the work in here, but that's our value of a, b, and c. So if we clear those and input those into our partial fractions, then what we get here for r is the integral from 1 to 3. I'm going to write in a slightly different order. So I'm going to write it as c over t plus 2 first. So c was 1, so we get 1 over t plus 2. Then I'm going to put the b term second. So that was 2. So I get 2 over t squared. And the reason I'm doing it like this is because we got a negative for a there. Okay, a was minus 1. So then finally, it was a over t. So that's going to be minus 1 over t. Okay, and this is all with respect to t. And hopefully at this point now, this looks a lot nicer to you. At this point here now, this is hopefully pretty straightforward integration. We've got our limits. We just need to integrate term by term. So this 1 over t plus 2 here, well, that's just going to give me the natural logarithm. This is the natural logarithm of t plus 2. Okay, so that's that first part there integrated. We've now got 2 over t squared, so that would be 2t to the minus 2. So remember, we add 1 to the power, divide by the new power. So in that case, that would give me 2 minus 2t to the minus 1, which is the same as minus 2 over t there. Okay, so we get minus 2 over t. And then finally, minus 1 over t, again, hopefully nice and straightforward. This gives us minus the natural logarithm of t. Okay, now our lower limit is 1, our upper limit is 3. And from here now, all we need to do is actually substitute our limits in. So remember, we start with the upper limit. So substituting the upper limit in first. So that's going to be the natural logarithm of 3 plus 2. So that gives me the natural logarithm of 5. And what I'll do is I'll put this all in one bracket first for the upper limit. We then do minus 2 over t, where t is equal to 3. So that's minus 2 over 3. And then finally, this is minus the natural logarithm of t here, where t is equal to 3. So that's minus the natural logarithm of 3. So that's the upper limit. We now subtract the lower limit off here. So we minus, again, substituting the lower limit in then. This is the natural logarithm of 1 plus 2, giving us minus ln 3 there. Oh, sorry. This part here is positive, but it will be minus in a moment. So that's ln 3 minus 2 over t. So if t is 1, that's minus 2. And then finally, this would be minus the natural logarithm of 1. But remember, ln of 1 is equal to 0. So we don't need to input that there. So that's what we get here. Okay, so that's what we get when we substitute the limits in. So all we need to do now is clean this up. Well, I get the natural logarithm of 5 minus 2 over 3 minus the natural logarithm of 3 minus the natural logarithm of 3, and then finally minus minus 2 gives me plus 2. Okay, well, I've got minus 2 lots of the natural logarithm of 3 here, so I've got ln 5 minus 2 lots of the natural logarithm of 3. I've got 2 minus 2 over 3. So in that case, that would be 6 over 3 minus 2 over 3, giving me plus 4 over 3. Okay. And then what I need to do here is simplify this. This is just lnb. Okay, so this is given as a single natural logarithm. Well, this 2 ln 3, we can write that as, so just put ln 5 back in here. This now using the power rule, we can write that as minus ln 3 squared plus 4 over 3, and then because this is a subtraction, we can write that as a quotient. Okay, remember ln 3 squared is ln 9. So what I've got here is ln 5 minus ln 9, which we can write as a natural logarithm of 5 over 9. Okay, so in that case, I get 4 over 3. Remember, it's a first, so it's going to be 4 over 3 plus the natural logarithm 5 over 9. Okay, and that's what we needed there. Okay, so it was a plus natural logarithm of b, so a is 4 over 3, so write that over here. We don't need to give it a, but I'll write them anyway. So a is 4 over 3, and then b is 5 over 9 there. Okay, so just make it clear. So that gets us the 7 marks. So like I say, it's they are quite long, these questions, with parametric integration, but the mathematics usually isn't too tricky. There's just lots of little things you've got to be careful of. Okay, so that gives us the solution there to part B, and we're going to have to clear the screen one more time to do part C. So we clear it one more time. So part C, we're asked to find a Cartesian equation of the curve C in the form y equals f of x. Okay, so what we've got here is our parametric equation. So we've got x equals the natural logarithm of t plus 2, and we've got y equals 4 over t squared. Okay, now given that we're asked to find the Cartesian equation of the curve C in this form here, y equals f of x, it makes sense that we substitute into this one here for y. Okay, so we're going to substitute in a value of t, or some form for t. And to do that, we rearrange this x equals here, and we make t the subject. Okay, so we want to make this t here the subject. So the first thing we need to do is get rid of the natural logarithm, and to do that, we take the exponential function of both sides. Okay, so that's going to give me e to the x, and on this right hand side here, that would give me e to the natural logarithm of t plus 2, and e to the natural logarithm, they're inverses, so they cancel, and I just get left with t plus 2. Okay, so if we want t as a subject, then t is simply equal to e to the x minus 2. Okay, and like we just said then, all we need to do now is substitute this t equals here into this equation of y, and then obviously we need to square it here. So therefore, y is equal to 4 divided by t squared. So t is e to the x minus 2, and that's going to be e to the x minus 2 all squared. Okay, and there we have it. So that's in the form y equals f of x. Okay, so I guess is the final 2 marks, and that gives us the solution there to question 9. Moving on to question 10 now, we have a question here taking a look at partial fractions and solving differential equations. So we've got 3 parts to this. Part A, pretty standard. It's essentially setting up the question for us. So we're asked to express 2 over p times p minus 2 in partial fractions. So let's just have a go at that to start with. So I guess this is the first 3 marks. So part A here, we want to express 2 over p times p minus 2 in partial fractions. So setting this up in partial fractions then, what this would be is this would be a over p plus b over the second factor here of p minus 2. So p minus 2. And to do this in partial fractions then, we just essentially get this over a common denominator. So this is going to be a times p minus 2 plus b lots of p, and that's going to be equal to the numerator here on the left hand side, which is 2. And what I want to do here is just eliminate one of the variables. So for example, if we let p equal 2, so if we let p equal 2, then this would be 2 minus 2 times by a, but 2 minus 2 is 0, so we get 0 here, the a disappears. So in that case, we can then just go on to solve for b. So this would give me 2b, so that's 2b, and that's equal to 2, and then we can just simply divide both sides here by 2 to get that b is equal to 1. So that gives us the value of b. We now want to just get rid of b, and to do that, we can just essentially set p equals 0. Okay, so if p equals 0, this disappears, the b disappears, and that's 0 minus 2 times a, so I get minus 2a is equal to 2. Okay, so minus 2a is equal to 2, and in that case then we just divide both sides by minus 2 to get that a is equal to minus 1. So if we then express this in partial fractions, I had 2 over p times p minus 2. Well, we said this is equal to a over p plus b over p minus 2. Now because the a was negative, that was minus 1, I'm going to put that second. So we're going to subtract that from b over p minus 2, where b is equal to 1. So this is 1 over p minus 2 minus 1 over p there. There's nothing wrong if you do put minus 1 over p plus 1 over p minus 2, but this is a nicer way of presenting the answer, but you wouldn't be penalised for presenting it in the original way as well. Okay, so that gets us the first 3 marks there. let's have a look now at part B. So, if we just click the screen here, just so we've got enough room, we've got a team of biologists is studying a population of a particular species of animal. Now, the population is modelled by this differential equation here, where P is the population in thousands. So this is important. Do take note of this. It can trip you up later on in the question if you don't kind of realise it. We know that T is the time measured in years since the start of the study. Then we've also got these initial conditions here, P equals 3 when T equals 0. And what we want to do in part B is go on to solve this differential equation to show that P is equal to this expression here. And it's 7 marks, so we would expect quite a decent amount of work here to get all 7 marks. So let's take a look at part B now. Now, on your advanced information, you know that differential equations goes with partial fractions. So your question is going to look pretty similar in the kind of layout. I'd imagine part A will be something to do with partial fractions, and then part B leads to the differential equation. And the reason for that is because part A helps set up the differential equation in part B. Okay, so if we just write the differential equation out first, I've got dp by dt is equal to a half p minus 2 cos 2t. Okay, so how does part A here, 2 over p times p minus 2, link to this differential equation here? Well, at A-level maths, when we're going on to solve differential equations, the only method that we know how to use to solve these differential equations is by separating the variables. Okay, so how do we separate the variables in this case? Well, the way to tell how you split the variables essentially is to take a look at this dp by dt. Okay, whatever variable goes in the numerator, so we don't really treat a differential as a fraction, but when we're separating variables like this, we're a bit naughty in terms of how we actually work the maths. So dp, that tells us that the p variables will be on the left hand side and then the t's will be on the right hand side. Okay, so in that case I need to get rid of this part here, so let's do it in a different pen color just to make it clear. So this part here underlined in red, that will go on the left hand side, and this part now, this dt here, that will go on the right hand side. Okay, so if we do that, then I'm going to divide both sides by 1 over 2 p times p minus 2. Now if you think about it, if you divide by this half first, then this would be the same as timesing it by 2, which is why it's 2 over p times p minus 2. Okay, so what that's going to give me then on the left hand side is 2 over p times p minus 2. So I've just divided both sides by half p times p minus 2. And I get 2 over p times p minus 2 dp. We would still have the dt here, but I'm now timesing both sides by dt. And this is why I said it's kind of, we're treating the differential in a way that it shouldn't really be treated as a fraction, but we do use it like this for separating the variables. So we times both sides by the dt. So what I get then is cos 2t dt. Okay, and the reason this works now is because notice on the left hand side this is just in terms of p, so we can now integrate this here with respect to p, and then same here on the right hand side but in terms of t, so we can now integrate cos 2t with respect to t. Okay, so that's exactly what we're going to do now. We're going to integrate the left hand side here, 2 over p times p minus 2 with respect to p. That should be a capital P, but just go with it, and then integrate the right hand side as well. So this is cos 2t with respect to t. Okay, and notice now how part A and part B links together. So if you wanted to integrate this here, we'd need to use the partial fractions to integrate it. Okay, and that's exactly why we did part A. So what I can do now is set up this left hand side here, this integral, using the partial fractions we found in part A. So this is going to be the integral of 1 over p minus 2 minus 1 over p. Okay, and that's with respect to p, so dp. And then if we integrate cos 2t, well, that would give me a half sine 2t. Remember, this 2t, if you were to differentiate that, would be 2. We divide by whatever that differentiates to. So that's a half sine 2t. And for the right hand side here, we do need the constant of integration, so that's going to be plus c. Okay. We didn't need, we do need this integral here still, but we have integrated this already, this right-hand side. Okay. Now, if I integrate this here, I kind of jumped, should have really put the integral here for cos 2t. I kind of jumped a little bit forward. But if I integrate this left-hand side now, well, 1 over p minus 2, that's nice and straightforward. That just gives me the natural logarithm of p minus 2. And if we integrate now minus 1 over p, that gives me minus the natural logarithm of p. Okay, and that's equal to a half sine 2t plus c. But notice we don't put the constant of integration on this left-hand side, only this right-hand side. Now, we've got two natural logarithms on the left-hand side. So they've got the same base. That base is the exponential function e. So what I can do is I can write that as a single natural logarithm. So I can write that as the natural logarithm of p minus 2 all over p, and that's equal to a half sine 2t plus c. Now, we've got our initial conditions, so because we've got those initial conditions, we can find the value of c. And if we just do the initial conditions over here, so we know p is equal to 3 and t is equal to 0. So in that case, if we just substitute p equals 3, t equals 0 in, we can then go on to solve for c. So that gives me the natural logarithm of p minus 2. So if p is 3, that's 3 minus 2 giving me 1 over p, which is 3. So I get the natural logarithm of a third. And that's equal to a half sine 2t. So if t is 0, that's sine 0. That's a half of sine 0 plus c. Now, a half times sine 0, well, sine 0 is just 0. So on the right-hand side here, I just get left with c. So what we can see then is c is equal to natural logarithm of a third. And we might prefer to write this as minus ln 3. Okay. Same thing. I think we might find it easier to use this form here, minus the natural logarithm of 3. So we're not done yet. There's still a bit of work to do to get it into this form here that we need to show in part B. So what I'm going to do now is write it in this form here with the value of c that we've just found. So what I'll do is I'll just clear the screen and we'll carry on with it. So clear all this. So what I've got then is the natural logarithm of p minus 2 all over p. Now we found that c was equal to minus the natural logarithm of 3, and that was on the right hand side. So if I take it onto this side, so that we've got all the natural logarithms on one side, that would be plus the natural logarithm of 3, and that's going to be equal to a half sine 2t. Okay, and notice this is looking pretty good at this point. We can see that we've got this e to the half sine 2t. We do have a half sine 2t. So we know we're kind of working on the right path here, but obviously we've just still got a few more steps until we get it into this form. Now, because we've got the natural logarithms on one side here, again, they've got the same base. This is the exponential function. Same here, the exponential function. We can again combine this into one single natural logarithm. So, because we're adding, we multiply. So this gives me the natural logarithm. Hopefully this doesn't get too confusing. So I'll put it all in one bracket here. So that's 3 times this part here. So it's going to be p minus 2 all over 2. Okay. And that's equal to a half sine 2t. And if we simplify this then, this gives me the natural logarithm of 3p minus 6. So we're just multiplying the numerator here with this 3. So 3p minus 6 all over, that should be p rather than 2. Not sure where that 2 came from. P minus 2 over p, 3p minus 6 over p there. Okay, so we've simplified the left-hand side. And again, this is equal to a half sine 2t. Now, if you can spot this, straight away, you don't need this middle line of working. If you just notice that you're times in by 3p minus 6 over p, that's absolutely fine. But I'm just trying to show as much kind of detail as possible, so hopefully we don't lose anyone as we're working through it. So what we're going to do here is solve for p. That's what we're looking to show here, that p equals 6 over 3 minus e to the power of a half sine 2t. So what I need to do now is get rid of the natural logarithm on the left-hand side. And remember, to get rid of the natural logarithm on this side of the equation, we take the exponential function of that. And whatever we do to one side, we do it to the other as well. So if I take the exponential function of the left-hand side, we just get left with what's inside the bracket. So I get 3p minus 6 all over p. And on the right-hand side here then, we get e to the power of a half sine 2t. Okay? So we've still got a bit more work to go here. Because I've got a 3p here in the numerator, we've also got p in the denominator, we're going to have to times through by the p and then collect all the p's on one side and factorize that p out. Okay, so I get 3p minus 6 is equal to p e to the power of a half sine 2t. Like we said, now we're going to collect the p's on one side, so that's 3p minus p e to the power of a half sine 2t. And that's equal to positive 6. So I've took this minus 6 onto the other side. And like we said, we need to factor out the p now. So I get p bracket. So that's going to be 3. P times 3 gives me 3p. And this would be minus e to the power of a half sine 2t is equal to 6. And then finally, if we just want p equals exactly as they've got it here, we just divide by 3 minus e to the power of a half sine 2t. So if we do that over here, therefore what we get is p equals 6 divided by 3 minus e to the power of a half sine 2t. And there we have it. So that gets us the next 7 marks, quite long, and it's very easy to make mistakes with these type of questions, but that was exactly as we needed to show there. So as required, or QED, whichever you prefer. So that's part B done. Let's take a look now, finally, at part C. And in part C, it says, find the time taken for the population to reach 4,000 for the first time, given the answer in years, to 3 significant figures. Now, for part C, even if you couldn't do part A and part B, for example, you can get the final 3 marks here. Okay, so for part C, we can attempt part C because we only need this answer here in part B. And seeing as they've given it to us, even if you couldn't do part B, you can still use this, okay? Now, the thing we've got to be very, very careful of here is we're looking for the time taken for the population to reach 4,000 for the first time. Now, P represents the population, but be very careful that you don't put 4,000 here. So 4,000 equal to 6 over this. That's incorrect. Notice that P is the population in thousands. Very easy mistake to make. So watch out for things like that in your exam. So what I've got then is 6 over 3 minus e to the power of a half sine 2t is equal to the population in thousands. So if we've got 4,000, this would be equal to 4. And what I want to do here now is solve for t. We're looking for the time taken. So we're looking to solve for t. So again, we're going to need to do a bit of work to get this into the correct form. But the first thing I'm going to do is get the power here of this t on the numerator. So I'm going to flip both sides of this equation. That's 4 over 1. We don't write it, but it is 4 over 1. So what I've got then is 3 minus e to the power of a half sine 2t all over 6 is equal to a quarter. I can now get rid of this denominator on the left-hand side by timesing both sides by 6. So 6 over 4 is the same as 3 over 2. So what I've got then is 3 minus e to the power of a half sine 2t is equal to 3 over 2. So that's 3 over 2. And I'm going to now take this minus e to the power of a half sine 2t onto the other side, make it positive, and I'm going to take 3 over 2 off both sides. Now if you've got 3 and you minus 1.5, you get 1.5, which is just 3 over 2 again. So therefore what I get is e to the power of a half sine 2t is equal to 3 over 2. Okay. Now we want this value of t, that's what we're looking to solve for. So we need to get rid of the exponential function. To get rid of the exponential function, we take the natural logarithm. So if we take the natural logarithm of e to the power of a half sine 2t, we just get left with a half sine 2t. So we get a half sine 2t, and then we take the natural logarithm of the right hand side, so that's the natural logarithm of 3 over 2. Okay. I can now times both sides by 2 here, so I just get sine 2t is equal to the natural logarithm of 3 over 2, we just need to times that by 2. So therefore, sine 2t is equal to 2 lots of the natural logarithm of 3 over 2. And then finally, we're just looking to solve for t here. So this is sine 2t. So we're going to take sine inverse of both sides. So therefore, 2t is equal to sine inverse of 2 lots of the natural logarithm of 3 over 2. And again, this is just something that we just need to use your calculator. So what you get here for 2t is equal to 0.9457, so on and so on. But obviously I just want t, so we just divide both sides here by 2. So I get t is equal, so I do 0.9457, so on, divide that by 2, and to 3 significant figures, what you should get here for t is 0.473 there. Okay, so that's 0.473 for the time taken for the population to reach 4,000 for the first time. Okay, and that gives us our solution there to part C and to question 10 overall. Taking a look at question 11 now, we have a question here on a geometric series. So part A is a little bit of a question on a proof. It's a pretty standard result, just proving the sum of the first n terms for a geometric series. And then part B is just a follow-up question, a bit of problem solving. So let's take a look at part A first and look at proving this result here. So we know for a geometric series, the sum of the first n terms would just be given by A, the first term, plus the second term, so that's going to be A times by the common ratio R, and then this would keep going on, so it's going to be AR squared, and this extends all the way up to the very last term. Okay, so that very last term is AR to the n minus 1. Okay, now if we think about this sum here to the first n terms, if we think about timesing that by R, what would we get? So what we'd get here is RSN, so this is the sum of the first n terms times by the common ratio, so we get RSM, and in that case then, because we've times the left hand side here by the common ratio R, we need to do the same to the right hand side. So my first term would be AR, essentially just adding an R to each of these terms essentially, so that's going to be AR squared, this would be AR cubed, and again this would extend all the way up to the last few terms. Now the penultimate term here would be AR to the n minus 1, and then the very last term here would be AR to the n. And what we think about here now is if we subtracted the first summation here, SM, if we subtract the second summation, from the first summation, what would we get? So what we'd get here is SM minus RSM. And in that case, if we think about this then, well, we'd subtract AR from this AR, so they'd cancel. This AR squared would cancel with this AR squared. This AR cubed would cancel with this next term here, and so on. And again, going up to the last few terms then, everything else in between cancels. This AR to the n minus 1, we subtract that from that one. And what we get left with then is just two terms here. We get left with A minus this last term here. So what we get is A minus AR to the n. Okay. Now at this point here, this isn't really anything like this. So we need to do a bit of work to get it into the correct form. So to start with, what I do now is I factorize on both sides of my equation. I factor on the left-hand side this Sn out. So what I get then is Sm on the outside of the bracket, and on the inside then I'd get 1. So Sn times by 1 gives me Sn. So I get 1, and here it's going to be minus R. So Sn times minus R gives me minus RSM. And on the right-hand side again, we look to factorize, and we can factor out the A here. Okay, the first term. So we get A lots of 1 minus R to the n. And at this point now, if we take a look at this line and compare it to what we need to prove, we can notice we're very, very close. Okay, they've got A times 1 minus R to the n. That's what we've got here. Perfect. They've also got this denominator of 1 minus R, and we haven't got that yet, but if we look on the left-hand side, we have 1 minus R. So clearly, all we want now is Sm. So therefore, Sm, well, to get just Sn on its own, I need to divide by this 1 minus R. So therefore, Sn is equal to A times 1 minus R to the power of m, and then we divide it by 1 minus R. Okay, divided by 1 minus r. And notice then we get the result that we need to prove here. So this is as required. Okay. So as required. So that gives us the first 4 marks there, giving us our proof. And then in part B, we're given that S of the first, or basically the sum of the first 10 terms, is 4 times the sum of the first 5 terms. We need to find the exact value of r. So, will I have enough room? I might just have enough room if we do it over here. Let's give it a go. So, what we need to do then is use our sum of the first n terms formula, but this case now we have the sum of the first 10 terms and the sum of the first 5 terms, but obviously this is 4 times that. Okay, so if we just start with S10 here, well, all I need to do then is simply replace n with 10. So what I get is a times 1 minus r to the n, where n equals 10, so that's 1 minus r to the power of 10. And then we divide this by 1 minus r, so we divide it by 1 minus r. And this is equal, well, this is 4 times the sum of the first 5 terms, so this is going to be 4 times, and now we just again use this formula here with n being 5. So this is a lots of 1 minus r to the n, where n equals 5, and we divide this by 1 minus r. Okay. So from here now, we need to do a little bit of work just to simplify this, and we need to go on to eventually solve for r. Well, the first thing we can do here is get rid of a. And the way we can get rid of a is simply by dividing both sides by a. And we know we can divide a because we're told at the beginning of the question that a can't be equal to 0. So it wouldn't cause any complications of basically dividing both sides by a. So what I do then is I divide both sides by a. So what that would give me is 1 minus r to the power of 10 over 1 minus r is equal to 4 lots of 1 minus r to the 5 over 1 minus r. Okay. And if we think about this now, as I've got 1 minus r as a denominator on both sides, if we times both sides then by 1 minus r, we eliminate the denominators and it becomes much easier to work with. So what I get then is a lots of 1 minus r to the power of 10 is equal to 4 lots of 1 minus r to the power of 5. Okay. So where do we go from here? Well, like we just said previously, we need to solve for r. That's what we're looking for. We're looking for the exact value of r. So at some point, we need to solve for r. Now, here, in this case, oops, we shouldn't have the a there. Ignore that. I was going to say what's gone on there. So ignore that a. I should have divided by that already. But this is correct up to here now. So 1 minus r to the power of 10. We obviously don't need these brackets. So let's get rid of them as well. So I knew I would make a mistake at some point. So there we go. So 1 minus r to the power of 10 is equal to 4 lots of 1 minus r to the power of 5. So it makes sense now to expand this right hand side here. So we get 1 minus r to the power of 10 is equal to 4 minus 4r to the power of 5. And what I want to do here now is get everything on one side and set this equal to 0 and see what actually happens here and see if we can actually go on to solve that. So this r to the 10 here would be the first term in this polynomial. So if we take that onto the other side and make it positive, we get r to the 10 minus, so the next highest polynomial is this power of 5 here, or this highest power would be 4r to the 5, so minus 4r to the power of 5. And then we've got 4 minus the 1. Again, taking this onto the other side, so 4 minus 1 gives us positive 3. So this is all equal to 0. And here now, we need to go on to solve this. So notice at the top of the question here, we must show all stages of your working, and solutions relying entirely on calculator technology are not acceptable. So we shouldn't really be using a calculator to do this. However, you can use a calculator to check that you've done this correctly. So what I want to try and do here, see if I can factorize this. If we can factorize this, then we should be able to get our exact value of r. And luckily, this does actually factorize. So if you split this into 2 brackets, then you need to think about what the first term will be in each of these. So for example, it could be r to the 10 on this bracket, and this one just being, in fact, that wouldn't even work, would it? That wouldn't work. So in this case, the only powers you can actually have then are 5 in the beginning of each bracket. So that's going to be r to the 5, that will also be r to the 5. And notice when you expand that then, adding the powers, you do get your r to the 10. I was going to say before it could be r to the 10 and r to the 1, but that wouldn't work because you'd get r to the 11. So the only possible options you can have then is r to the 5 and r to the 5 in both brackets at the beginning. And then we just need to obviously times to get this 3, but adds and simplifies to give minus 4r to the 5. So in that case then, this would just be minus 1 and minus 3. Okay. When you want to simplify this here and expand it, you should get the exact same as what you did here. So this is all equal to 0. So here now, what we get is actually two solutions. So there should be a bit of an issue here because notice this is just the exact value of r. So it's just one value. However, here this indicates we've got two solutions. We've got r to the 5 equals 1 or r to the 5 equals 3. Well, if we take the fifth root here, so that would give us r, that would give us the fifth root of 1. And the fifth root of 1 is simply 1. However, we're told at the beginning of the question, r isn't equal to 1. Okay, it would obviously cause issues with your summation here if you get a denominator as 0. And clearly a geometric series isn't a geometric series if the common ratio is just 1. Okay, so we carve this solution here, r cannot be equal to 1. Okay, so we omit this solution here and we just find this solution here. So again, taking the fifth root of both sides, that would give us r on the left hand side, and on the right hand side, it's the fifth root of 3. Okay, and there we have it. We don't want the decimal of this, we just want the exact value. So therefore, we found the exact value of r. Okay, so that gives us the solution to part B and to question 11 overall. Moving on to question 12 now, we have a question here on differentiation with parametric equations. And it's split into two parts. Part A is hopefully quite nice and straightforward, just gets us 2 marks. And then part B involves the differentiation. So let's just start with part A here first and find the value of theta at the point P. So we've got our parametric equations here. We've got the point P, which lies on C, and it has these coordinates. So if we want to find the value of theta at the point P, then we need to use either of these parametric equations because we know the x and the y coordinate. In that case, then we can simply substitute it into either x here or y. With this just being root 3, I think it's easier just to substitute this into x here, but it doesn't matter if you substitute root 3 over 2 here into y, and then take sine inverse on both sides. That's absolutely fine as well. But I'm going to start with tan theta is equal to root 3. Okay, so this is part A. So tan theta is equal to root 3 because the x coordinate is root 3. So root 3 is equal to tan theta. So in this case, we just want theta, the value of theta. So we take tan inverse of both sides. So tan inverse of tan theta. And then we take tan inverse of the right hand side as well. So tan inverse of root 3. Well, tan inverse of tan theta just gives us theta. And tan inverse of root 3 gives us pi over 3. And make sure you're in radians here. Notice theta is between 0 and pi over 2, so make sure your calculator is in radians. Okay, so that gives us the solution there to part A, giving us the value of theta being pi over 3. So that's part A done. Let's take a look at part B now. So we're told the line L is a normal to C at P. The normal cuts the x-axis at the point Q. And we can see that here from the sketch in figure 3. And what we're going to do is show that Q has these coordinates, so k root 3 and 0. Now, clearly the y coordinate will be 0, because that's where it cuts through the x-axis. You know, when it cuts through the x-axis, the y coordinate will always be 0. So we're going to use that to our advantage in a moment. But to start with, as we're talking about normals here, so the normal to C at P, we know we're going to need to use differentiation here. So what I'm going to start with first is differentiating x here with respect to theta. Then we differentiate y with respect to theta, and then we can go on to find dy by dx. So if we differentiate x here with respect to theta, so dx by d theta, well, tan theta, you can just find this in your formula book if you can't memorize the result. But if you differentiate tan theta with respect to theta, that gives you sec squared theta. Okay, so that's sec squared theta. And we now differentiate y here with respect to theta, so that gives me dy d theta. And dy by d theta, well, differentiating sine theta with respect to theta, that's a nice easy result. Just gives us cos theta. Okay. But we want dy by dx. So for dy by dx, that's simply going to be dy by d theta. So dy by d theta. And then we times this by the reciprocal here of dx by d theta. So 1 over dx by d theta, which would give us d theta by dx. Okay, and notice here these d thetas would cancel, and what we would get is dy by dx. So in that case then, dy by d theta, well, that's cos theta. We already know that straight away here. D theta by dx, notice that's the reciprocal here of dx by d theta. So in that case, that's going to be times in it by 1 over sec squared theta. Okay. So now what I've got here is cos theta all over sec squared theta. So cos theta all over sec squared theta. And remember, for sec theta and sec squared theta, this is the same as 1 over cos squared theta. So what I've got here then is cos theta all over 1 over cos squared theta. Okay. And when you've got something like this, so you've got cos theta divided by this fraction here, where it's 1 over cos squared theta, then what I'm going to end up with is cos theta times cos squared theta. So cos theta times cos squared theta, that gives us cos cubed theta. Okay, and what that represents here is dy by dx. So this is dy by dx. So if we know the value of theta at this point P, then we can find the value of the gradient. Okay, so we know the value of theta at the point P. That's what we found in part A here, and this is why these two parts kind of link quite nicely. So we know theta is equal to pi over 3 at the point P here. Okay, that's what we found in part A. So therefore, dy by dx, so dy by dx is equal, in this case then, to cos of pi over 3, so cos of pi over 3 all cubed. So we know what dy by dx is, that's cos cubed theta. So if theta is pi over 3, then this is our result. And all we need to do is put this into our calculator. And what I get here is 1 over 8. Okay, so we get 1 over 8 there for dy by dx. But we have to be slightly careful here. So the line L is a normal to C at P. So we're not using this as our gradient, as our M here, but we want to take the negative reciprocal. So flip this fraction and times it by -1. So the perpendicular gradient here is -8. Okay. So now we've got the value of the gradient that we're using here for our normal. We've got the point P here, so we can easily find the equation of the normal now. What I'm going to do is I'm just going to clear the screen, just so we've got enough room for this. So we carry on with part B up here. So we're using now y minus y1 is equal to m times x minus x1. Okay, so y minus, so what's x1 and y1 in this case? Well, x1 is this root 3, and y1 is this root 3 over 2. So that's minus root 3 over 2 is equal, so remember m was the -8 we found here, so that was -8 times by x minus x1, which is root 3. Now, we're looking for the coordinates here of q, and this is where it cuts through the x-axis. And remember, it cuts through the x-axis here when y equals 0. So if we set y equal to 0, then we can go on to solve here for x. So this is minus root 3 over 2 is equal to minus 8x. So it's -8 times -3, so that's going to give me positive 8 root 3. So plus 8 root 3. So now, like we said, we're just going to solve for x here. So I'm going to take this -8x onto the other side, make it positive. So I get 8x, and this minus root 3 over 2, I'm going to take that onto the other side. So what I get then is 8 root 3 plus root 3 over 2. Okay. So, whether you get this over a common denominator or you just times everything through by 2, doesn't matter which way you do this. But essentially what I've got here then is 16x. So 16x is equal to, that'd be 17 root 3. And then finally we just want x here, so we divide it by 16. So x is equal to 17 root 3 all over 16 there. Okay, and that's our x coordinate. So notice we've got the root 3 here. So what's the value of k? Well, in this case, k is equal to 17 over 16. Okay, that's our coefficient there. So That gives us the value of k there, gives us the solution to part B, and the solution to question 12 overall. Moving on to the very last question then in this predicted paper, we have question 13. And question 13 here has a lot of context to it. It looks quite tricky. And we've even got this diagram at the top here essentially of our problem. However, for part A, we don't actually need much of this information. In fact, we don't really need any of it. All we need is the actual question. So for part A, we're asked to express 24 sine theta plus 7 cos theta in the form r cos theta minus alpha. So let's just write down part A here. So this is a pretty standard type of question. You've probably come across many of these in your past paper revision and just general revision in class. There's just something to be very careful of with this part A and this type of question that they've given us. So what we've been asked to do is express 24 sine theta plus 7 cos theta in this form. So it's r cos theta minus alpha. Okay, and we just have to be slightly careful here. Remember, if you've got something of the form r cos theta minus alpha, then this is equivalent to a cos theta, so a cos theta plus b sine theta. Okay, now if we just take a look at what we've been given, what we've got here is b sine theta plus a cos theta. So they've just kind of done it essentially just to try and catch you out here. So it's just one of these things you've just got to be slightly careful of. So in that case, let's just write it the correct way here. So that's 7 cos theta plus 24 sine theta is equivalent to r cos theta minus alpha. Okay, and from here now what we can see then is that we've got a here equals 7, so a is 7 and b is 24, so b is 24. And what we want to do now is we want to find r and we want to find alpha. So to find r, this is pretty straightforward. This is just the square root of a squared plus b squared. So that's a squared plus b squared. And if we just put this into our calculator then, we get the square root of 7 squared plus 24 squared. And if we put that into our calculator, what we get here is r equals 25. So that gives us r there. We now need alpha. So we need alpha, and to find alpha, we do tan inverse of b over a. So b over a. So in that case then, using our values of a and b here, this is going to be tan inverse of 24 over 7. Okay, and again, put this into our calculator. Notice here that alpha is between 0 and 90 degrees, so make sure your calculator is in degrees mode. And what you should get here for tan inverse of 24 over 7 is 73, and 2 decimal places as we're asked to do here for alpha, 73.74. So 73.74 there degrees. Okay, and all we need to do now is make sure we just give it in the correct form here. So what we've got then is 25 cos theta minus 73.74 there. Okay, notice this is your r and this is your alpha, so I've just given it in this form here. Okay, so there we go. So that's the first 3 marks there. Hopefully not too bad, just being careful with that little trick here at the start. Let's take a look at part B now. And what I'm going to do here is I'm just going to clear the screen just for part B, and hopefully we should get C on at the same page as well. So if we just clear this, let's take a look at part B now. And in part B, we're told that theta varies. What we're going to do then is find the minimum value of V. So we're looking for the minimum value here of this fraction. Okay, and if we notice, again, you don't really need to understand what V is. I would definitely recommend reading this context, but you don't need to understand what V represents to actually go on to solve part B. So what I've got here is this fraction, 21 over 24 sine theta plus 7 cos theta. And notice this denominator, 24 sine theta plus 7 cos theta, is exactly what we had in part A here. And notice we give it in this form. So what I can do now is rewrite V in that correct form, or, well, alternative form, I should say. So what I've got then is V equals 21, and this is over. So this was r cos theta minus alpha, so we had 25 cos 25 cos theta minus 73.74 degrees. Now what I want to do here is I want to find the minimum value of v. So what I'm looking for is min v. Okay, we're looking for the minimum value of v. Now because this is a fraction, the numerator is just a fixed value. We can't affect that, so that would just be 21 still. However, for the denominator then, if we're looking for the minimum value of v, then what I want to do is I want to make my denominator as large as possible. Okay, so we're going to make the denominator as large as possible. So in that case, we find the max of the denominator. So this is the max of the denominator. I can't spell, so I'm just going to put denom, but hopefully you understand that's just the denominator. So how do we make the denominator as large as possible here? Well, what I've got is 25 times the cosine of this angle. Now, if we just think about the cosine function here, and we just draw a quick sketch, don't have to be anything perfect, just so we can see what's actually happening here with cosine, then this axis here is theta, this axis here is my y-axis. And if we think about cosine, sketching cosine, it starts with a height of 1. It's going to come down. It's going to have a minimum value of -1. And it's going to look something like that. My sketch isn't perfect, but you get the idea. We've got its maximum value of 1, and we've got its minimum value down here of -1. Okay? So, in that case, if I want to make this denominator as large as possible, then the maximum value I can take for cosine is this 1 here. Okay? It's going to be 1. So that will always be 1. This part here will be 1. This is equal to 1. So what I've got then is 25 times 1. That's how we maximize the denominator here. So what I've got then for the minimum value of v, so min v is 21 divided by 25 times 1, giving me 21 over 25 there. Okay? And that gives us our solution there to part B. So that's the minimum value of v, given that theta varies. So that's part B. So that's 2 marks. Let's have a look at part C now, which essentially follows on from part B. So part C here. So we're given that Kate's speed has the value found in part B. So we know Kate's speed is this value here, 21 over 25. So what I want to do is I want to find the distance AB. So we now need to look at the diagram that we've been given here. So we've got the point A here. We've got this point here, B. And what I want to do is I want to find this length. Okay, that's what I'm looking for, this distance. So we're looking for this distance. So how would I do this? Well, the first thing I notice here is I've actually got this triangle. And given that this here is a right angle, it means this here will also be a right angle. So therefore, what I've got is a right angle triangle. And if I've got a right angle triangle, and we're looking for a length here, we should be able to use either Pythagoras or trigonometry to find this length here. And given that we've got this value theta, what we'd hopefully be able to do here is find the value of theta and then use trigonometry. Okay? So, where do we begin with this? Well, we know v, like we just saw here, is the value in part B. So we know v is 21 over 25. Okay? So, when we had a value for v being 21 over 25, that's when cosine of theta minus 73.74, that part was 1 here. That was the maximum value of cosine. So in that case, what I've got here then is cosine of theta minus 73.74 degrees is equal to 1. But remember, this here, for this to be equal to 1, this must be cosine of 0. So this is cosine of 0, that's equal to 1. So therefore, what I've got here then is theta minus 73.74 is equal to 0. And from here then, we can clearly just solve now for theta by adding 73.74 to both sides. What I get then is that theta is equal to 73.74. Okay? So what I'll quickly do here is just sketch this triangle out again. Let's do this in a different pen colour just to make it nice and clear. So if I sketch this, it might look something like this. Okay, mine's not perfect, but this is the point A here, this is the point B, and we're looking for this length. Like I said, this is a right angle triangle. And we now know this angle here, so we can just go on to apply trigonometry. So this is 73.74 degrees there. Okay. So in that case, we also know this length here as well. Again, if we just look at our diagram here, this length is 7. Okay, so this length here is 7. So we've got our length, we know this angle, and we want this length here. That's what we're looking for. Give that a question mark. So we can now just apply basic trigonometry. We're just going to use SOHCAHTOA. So it sounds kind of a bit, you know, you probably find this quite easy at this point, but if I just write out instead, SOHCAHTOA. So what I've got here is I've got the opposite. This is 7. That's the opposite here. And what we're looking for is the hypotenuse here of this triangle. So this is H. So that's what we're looking to find. So I've got the opposite. We want the hypotenuse, so that means we need to use S here. We're looking to use sine. We know the angle is 73.74 degrees. So what I've got here then is sine of 73.74 degrees. This is equal to opposite divided by hypotenuse. So this is the opposite 7 divided by this length here, which you can either assign it a variable, or I'm just going to call it AB. That's the length AB. So this is divided by AB. So in that case, what I want now is AB. We're looking to find that length. So I could times across both sides here and get AB sine 73.74 degrees is equal to 7. And therefore, if I want AB, we do 7 divided by sine of 73.74 degrees. And I'm running out of room a little bit here. So if I just give the solution here right at the top, so this is where my solutions were now top right, then if you put this into your calculator here, 7 divided by sine of 73.74, then what you get is, if I give it to 3 significant figures, is 7.29 there. Okay, and given that we're working in meters here, this will be 7.29 meters. So there we go. So that's part C. Like you can see, you know, there's a couple of tricky parts that you've got to watch out for. So that gives us the next 3 marks. And then finally, we arrive at part D here. So, again, let's clear all this just so we can finish part D. And for part D here, we're given that Kate's speed is 1.68 meters per second. And what we're going to do is find the 2 possible values of the angle theta, given that theta is between 0 and 150 degrees. So we refer back now to our formula for V here, where we know V is equal to 21 over 25 cosine of theta minus 73.74. Okay, we're using this formula for V. Now, if we're saying that V is equal to 1.68, then what I've got is 1.68 is equal to 21 divided by 25 cosine theta minus 73.74. All I've done then is just took my formula for V and set it equal to 1.68. If we're told that Kate's speed is 1.68, then we can just put them equal. And what I want to do here now is essentially just solve for theta from here. So the first thing I can do is flip both of these. So what I'd get then is, so if I just write it, what I'm going to do is I'm going to put the cosine on the left hand side. It doesn't particularly matter, but just so it looks a bit neater. So I'm going to get 25 cos theta minus 73.74 degrees. That'll be over 21. That's over 21. And that's going to be equal to 1 over 1.68. So 1 over 1.68. We've just flipped that side as well. And now we're going to times by 21 and divide by the 25. Remember, I just want to isolate this cosine theta minus 73.74 here. So like we just said, we're going to get cos of theta minus 73.74 degrees. That's going to be equal then to 21 all over 25 times 1.68 there. Okay, and this works out quite nice. What I actually get here on the right hand side is 0.5. So what I've got is cosine of theta minus 73.74 degrees is equal to a half. Okay, and that's really nice here now, because what I can do then is take cosine inverse of both sides. So I get theta minus 73.74 degrees is equal to cosine inverse of a half. And cosine inverse of a half is 60 degrees. So I've got theta minus 73.74 degrees is equal to 60 degrees. And what we'll also have here is I will have a second solution. Now, if we use a cast diagram to take a look at this, you can sketch the cosine function as well to do this. I'm going to use a cast diagram, but it doesn't particularly matter whichever method you are most familiar with, works absolutely fine. So the first angle here, we're going to have here, so that's from here to here. So this angle is 60 degrees. And where I'm also going to have a cosine solution is in this quadrant here. And this one is going to go like this. So this will be minus 60. Okay, so this is minus 60 degrees. Okay. So our second solution, like we said here, will be minus 60 degrees. And we've also got to account for this minus 73.74. We just want the value of theta. That's what we're looking for, the two possible values of the angle theta. So therefore, what I've got then is, if we just write our solutions for theta here, so therefore theta, well, this is going to be equal to 60 plus 73.74. So 60 plus 73.74, that gives me 133.74 degrees. And we're in the range here that we're saying for theta, so 0 to 150 degrees. And I've also got minus 60 plus 73.74. And again, just put that out in your calculator, and what you get then for theta is 13.74. Okay, and there we have it. So those are our two possible values of the angle theta, given that theta is between 0 and 150 degrees. So that gives us the solution there to part D, gets us the final 6 marks, and that completes question 13. So like I said, definitely not an easy question. There's a couple of tricky parts in that question, but hopefully you find that quite a nice challenge. And that finally brings us to the end of this predicted paper. So, like always, I hope you found the paper helpful and this video. Please leave feedback. Hopefully you find the paper not too easy, not too challenging, but maybe, quite a nice balance. If you did notice any mistakes, I could have very well made some. Please leave a comment down below, just help others as well. And I'll obviously make sure to give them a heart if you have found my mistakes, because that's very much possible. But other than that, good luck for the upcoming exams. I'm sure you'll all do great. And yeah, keep revising. Cheers.